This video is the first in the series of electrochemistry and is on oxidation and reduction. So oxidation is defined as the loss of electrons and reduction is defined as the gain of electrons. So an easy way to remember this is oil rig. Oxidation is loss of electrons and reduction is gain of electrons. Okay, so the oxidation and reduction refer to the reaction itself, but you may also have heard of the terms oxidizing and reducing agents. Now, an oxidizing agent gains electrons, so is reduced. It's known as an electron acceptor. A reducing agent loses electrons and is oxidized and is known as an electron donor. So examples for an oxidizing agent is oxygen, or O2, and the example for a reducing agent is NaBH4, which is used in reduction reactions, or metal catalysts like nickel used in hydrogen reduction. Now, a redox reaction is one in which an oxidation and a reduction has taken place. So if we look at the example here between copper and silver, we can see that this net ionic equation shows that copper has lost 2 electrons. Its oxidation state has been increased by 2, so we've gone from 0 to +2, and this means it has been oxidized or is a reducing agent. Similarly, with silver, we can see that it has gained 2 electrons. Its oxidation state has decreased, so it must be an oxidizing agent as it's been reduced. Redox reactions are made up of half reactions. So in this case, we have copper has formed copper 2+ ion, which is aqueous, and 2 electrons, and silver has gained electrons to form silver solid. So the important thing to remember is that you balance the redox equation. So redox equation is made up of half equations. The number of electrons must match. So here we've put a 2 in front of everything so that there's 2 electrons gained by the silver and 2 electrons lost by the copper. Redox reactions and half reactions can be applied in terms of electrochemical cells. So here we have a standard hydrogen electrode. So one thing to remember with the standard hydrogen electrode is standard conditions. So standard conditions are 1 atmosphere of, in this case, hydrogen gas, 298 Kelvin or 25 degrees Celsius, and 1 molar or 1 mole per decimeter cubed of solution. So in this case it will be H+ ions, which could be, for example, hydrogen chloride. The standard hydrogen electrode is what all half reactions are compared against. It's the standard electrode potential. Its standard electrode potential is arbitrarily set to 0. It's the reference electrode, if you like. When a half cell is coupled to a standard hydrogen electrode, the hydrogen cell is always on the left. So whenever you're drawing 2 cells together, the hydrogen cell is always on the left. The electrode potential, the standard electrode potential, is the electrode potential of a half cell minus the electrode potential of a standard hydrogen cell. It's a way to measure how easily a substance loses electrons. A half cell can either be a gas with a solution of its ions, as in this case with the hydrogen half cell that we have here, and this is platinum. The platinum electrode allows electrons to enter or leave the solution. Alternatively, you could have a metal electrode in a solution of its ions. This will be, for example, copper solid in a solution of its insoluble salt. What we have here is an electrochemical cell. So we have two different metals in two different solutions of their ions. We have zinc solid with zinc sulfate, and we have copper solid with copper sulfate. Again, these are standard conditions, so 1 molar of each solution. We have a salt bridge made up, in this case it's KCl. The salt bridge shouldn't react with either ions in solution. The direction of electron flow is from zinc to copper, the anode to the cathode. Here you'll see how the cell is represented as an equation. So a single line is a barrier between two phases, so a two-phase barrier. And a double line is a barrier between two cells, so a two-cell barrier. And this is how you draw the equation. So you have your solid on the outside and your aqueous ions in the middle. The electrode potential of any electrochemical cell is also known as the redox potential, and is the voltage of the cell on the right minus that of the cell on the left. So it's represented by this equation here. And stronger oxidizing agents like oxygen have a higher, more positive redox potential.